ColdSpark. I remember when we started the project and we had a discussions with Professor Shin-Tu at the University of Liverpool. And he said, this is not a scientific expression. You can't use ColdSpark because it is not science. No, it is correct. It is marketing. It is sounds cool. That's it. It doesn't need to have a bare meaning. But it's also a testament to the legacy of the company, because Side has been working with cold plasma or non-thermal plasma since 1997. So it's a testament of cold plasma and the new potential. And cold is also just to make sure it's binary concepted, yeah? Because all of the other variants of methane pyrolysis, those are thermal, those are warm. So we wanted basically with ColdSpark not to mimic what others have done. We want to tread new ground. So we wanted to do the limbo. How low can we go? So the idea here, when we dissociated this molecule first time to produce the carbon, we had a reactor temperature of 7 degrees centigrade, so 70 degrees. And the people I talked to in Sintef or other places said, you can't do it. You need 1200 degrees. And we say, we beg to differ because we rely on towns and avalanches, not thermal decomposition. If we go back to, this is what we presented when the ambition level for ColdSpark 3 years ago. So we said we want to make a modular, low-scale, containerized solution. The reason for that is we did not have the funding to make something which is $1 billion. So we had to be realistic. We couldn't make something which is, 40 tons a day or something, grand scale, which would be Shell or Equinor. We said we need to be realistic in doing this. And this is the ambitions we still have. You will later today have a look at the system. You will identify all the core features of the systems which you see depicted on the photo. Yes, we are not connected directly to the gas grid, but we do connect to the electricity grid. So that's the biggest difference from this. You will see the power systems, you will see the reactor systems, you will see the carbon separation systems, and so on. So you get to see what we have been doing. This was the original sketch and the ambition we had for the project as such. I can say straight away, the biggest challenge of the project is to handle large amount of the elemental carbon. A lot of people believe this is going to be a problem handling the hydrogen. No, it's not. The carbon is the biggest challenge. I can mention we have two sister projects in the EU. Project Storming and Project Titan. When we started our project, we aimed high. It's more like we said, we are going to jump 2 meters and 45. This is basically world record level. Our competitor said, let's keep that as low as possible. Let's produce with an ambition level of 6 grams of hydrogen per hour. That's our competition, and 50 grams. They got the same funding. So it's an interesting scenario. So that was the ambition level. And this is what we're still aiming for, not for the EU project, but long term. Just to understand, the EU project brought us to TRL 5. We've been always thinking about how to get to TRL 9 if there's a market still. Why are we doing this? This is the main reason why we are trying to do this, because we do think the existing grid of natural gas in the world, in Europe, in US, in India, in China, you have invested trillions of dollars with an existing natural gas network. We do believe the best way of transporting hydrogen is in the form of methane, where you have made the investments and you can convert last mile hydrogen when and where you need it. So using this molecule, which is, when you weigh this molecule, it's 25% hydrogen. So when people talk to me about, blending in hydrogen in pipelines, it's already 25% there already. That's how nature made it. There's a reason for nature made it that way. So we don't need to blend, it's already there. So let's use that in the best possible way. And the second part of the equation is, of course, the carbon intensity. If you don't burn this, the problem politicians face when I meet them is they say, well, this becomes a climate problem. Yeah, if you burn it. Yeah. If you don't burn it, you remove the methane permanently from the cycle, and you don't produce the CO2, and you have valuable material. So it's about changing the mindset completely and understanding the value of this one, the carbon atom becoming a solid particle. And that is hard for people to understand, because we are seeing a transparent gas becoming a black material. It's difficult for people to understand how can that happen. But when they see it in real, they accept it, even if they don't understand it. So we have an ambition for the future. We think it's possible to scale the technology, but going slowly. What we see in the market is a lot of uncertainty. There's a skepticism with investors. The green hydrogen hype is slowly fading away. It's being replaced with something more pragmatic in terms of, it needs to be affordable, it needs to be scalable, and needs to be clean. Bjarte will dive into that, but those three things does not come together today. So green is way too expensive. So if we do it, we need to, take the money from someone else. So it's the hospitals going to suffer, it's the elderly going to suffer, society going to suffer. We can't gamble on something that is so expensive. So this is why we do think we had a possibility. And I want to say location, location, location. Anyone that have a store or visiting store knows that's important. Being in Norway is so important that a lot of people don't understand it. They think it's about technology. No, it's not. It's about being in Norway, because in Norway we have access to low carbon methane, natural gas. It's the lowest in the world.
ColdSpark to break this trilemma, generating two revenue streams by producing valuable carbon and also hydrogen, targeting costs down to the levels of SMRs. No CO2 emissions directly from the process itself. It just relies on clean energy and much less energy required than the current green hydrogen. It's built as a scalable modular design, so you don't need to go to massive scale immediately. It can be distributed to be close to where hydrogen is needed, and so we don't have the big geological constraints when building big blue hydrogen plants, which needs to be close to off-loading points for the CO2. How do we do it? So we have created the three pillars. So we have a novel reactor that combines the efficient gliding arc mechanisms with Corona technology that's more scalable to have a larger, more uniform plasma field. To power it, we have created an advanced power supply that's able to control this plasma and the different regulation modes needed. And we have created an integrated loop connecting all the parts needed together to create a very efficient system. So the first novel reactor combines the known gliding arc principle, creating one arc that's quite high temperature and a small volume to effectively dissociate anything you put through it. But it's difficult to scale. The more power you put into it, the smaller it gets, and everything just gets very complicated. Electrode wear is high. And then we have the Corona discharge, which we have been using in our non-thermal plasmas, where each cell can operate in parallel with the other cells. They don't affect each other, so it's easy to scale. But the energy density in the Corona plasma is a bit low for doing direct methane cracking. So that's why we have developed the ColdSpark reactor. That's a more hybrid design that combines the higher density of the guiding arc with the scalability of the corona discharge. So just simple depictions of them, not to reveal too much details. And then there's the integrated system, where we go from the reactor, where we have an internal recirculation loop kept inside the reactor to stabilize discharge and gas distribution inside the reactor, creating a lot of carbon that is taken out directly in the reactor. And the rest is taken out by a carbon collection system, compacted into pellets for easy storage and transportation. And then the PSA system that extracts the hydrogen, recycles the methane and other impurities back in the reactor to ensure that we are cracking all the methane. So no water is needed, like other technologies. No catalysts that wear out, that needs to be replaced. And it's a modular design that allows you to create it in different scales. So during the project, we've gone all the way from the small benchtop models running to testing just the reactor, and to the end to putting together the integrated system to show the whole process running together.
Transforming to gas and do cleaning to PSA.
Yeah.
You don't want to bring the problems to the PSA.
No, so remove them as early as possible.
And I go to the carbon.
Yeah. Yes?
Yeah.
Yeah.
What is the main advantage other than methane pyrolysis processes used to
When you use catalysts, you always risk poisoning the carbon. You will always get some catalyst carryover. So either you have to be very clever and find a carbon-based catalyst that won't pollute the end product, or else you always have the problems of separating the carbon and the catalyst and deactivation of the catalyst. And when you go to a pure thermal system, you have the problems of wear in the system, because then you need very high temperatures, many thousand degrees, typically to get a very efficient process, and that keeps a very operating issue.
Yes. In the test facilities in Tananger, how are you going to deal with the gas stream coming from Austria? Is it if you remove impurities? Because there are some CO2 and might be also some mercury. And you never know.
No. So at the current stage, we rely on the normal ways of cleaning the gas. So we also have access to the LNG plant, which can supply clean methane. So we consider that the pre-treatment of the gas, that's a known technology. So that is not the main focus of this research project. Yes, so there will be, depending on the funding and the scale, so that would need to be in place. Yeah.
How do you handle the carbon here? How do you make it into a soluble product that has a certain size and a certain quality?
That's part of the ongoing research to qualify the carbon for different applications, so that the later presentations will go into more detail. But the current carbon collection system has an integrated compression system that takes this very fluffy carbon that's produced and compacts it down to a more manageable state. So
Particle size that you...
Yes, we have seen that different experiments setups, we can produce different kinds of carbon. So Sachin will get into that in his presentation. Yeah.
Is the carbon very sticky?
No, it's extremely fluffy. So I think we have some small samples.
We can sit around us. Please don't.
Yeah. So we can start here. So not sticky at all. And we also have a DC offset in the plasma reactor, so that creates an electric field that removes the carbon particles out of the active plasma zone. And that also doesn't stick to the walls. It's very, very light attraction forces.
How will magnetic process work? Can you electrostatically charge?
Yes, so this is very easily electrostatically charged. So using a DC offset in the plasma will effectively remove the carbon out of the active plasma zone. So it won't hinder further operation. So.
Thank you.
Thank you.
All good question. This is really interesting. All good questions, and this will keep you curious to the next presentation.
Shin-Tu of the University of Liverpool, and our group was leading Work Package 1 development and optimization of plasma methane cracking process at lab scale. So as Beate mentioned, the current main method of producing hydrogen is the steam reforming of natural gas, and it's high direct CO2 emissions, but it has a low minimum energy demand. There are several other options to do it. One of them is water electrolysis, no direct CO2 emissions and directly from water, which is nice, but the minimum energy demand is significantly higher than that of steam reforming. So it makes it challenging to switch over to that one. Another option is methane pyrolysis, which is methane to hydrogen carbon. To do this, we prefer to use plasma, so electricity to crack the methane into hydrogen and E-carbon. We use non-thermal plasma using no catalysis, so no precious metals, and also at low temperatures and atmospheric pressures. And the carbon can be very useful, for example, for use in tires or batteries. So Work Package 1, providing key system parameters for the design of the large-scale prototype at site at TRL5. And to do this, we're designing and testing some 2 lab-scale prototypes, investigating the effect of the key parameters of the reactor, power supply, and operation parameters on the KPIs, and understanding the effects of the impurities in the gas source on these KPIs, and getting new insights into the reaction mechanisms in the plasma methane cracking process. So we're leading on lab-scale testing, evaluation of the impurities and plasma reaction mechanism, and supporting on carbon material analysis and reactor design as well. So in our lab, we use a slightly different one to decide because this was the preliminary work. So we use 2 different systems. This is the most optimal one. It's a rotating gliding arc reactor where the methane is fed from a bottle tangentially into the reactor with a cone shape inner electrode, which is the high voltage electrode. We use an AC high voltage power supply, and a tube on the outside is the ground electrode. We monitor the electrical signals with a high voltage probe and a current probe, and then use an oscilloscope to analyze those. And we analyze the gas products on the outlet with the GC. We've used a variety of carbon capture methods, and here is some of the carbon that we produced from one of our plasma runs. We've primarily tested the effect of the discharge power, the impurities, the flow rates, with a fixed discharge frequency and a fixed minimum discharge gap. So looking at the effect of the flow rate and the power, these data are anonymized because we're going to publish a paper on this soon. So if you want to see the figures for what the flow rates and the powers are, please go to read the paper. So the effect of the flow rate needs to be balanced to balance the resonance time along with the size and the stability of the arc. You'll notice from the energy consumption for both the hydrogen and the methane at the lower flow rate, the energy consumption is very high because the arc is not stable at that flow rate. Finally, for the power, as you increase the input power, it's good because the conversion increases, which is what we expected. But the good thing is the selectivities of all of the products and the energy consumptions didn't change. And our optimal results are for the optimal parameter is a 6.8% methane conversion, 14 kilowatt hours per kilogram of hydrogen, and a carbon selectivity of 83%. So looking at the effect of the impurities, we've tested 3 impurities: nitrogen, water, and carbon dioxide. Nitrogen had no effect on the methane conversion, but negatively affected the hydrogen selectivity, energy cost, and energy efficiency. And the other 2 also negatively affected the methane conversion, as well as negatively affecting the hydrogen selectivity, energy cost, and energy efficiency. This is because they kind of interact in the plasma in a slightly different way. So there are more side reactions, creating more higher hydrocarbons, which takes the energy away from methane cracking. So benchmarking this against some other hydrogen production technologies, our work got a pretty good energy cost for hydrogen production and high energy efficiency with no direct CO2 emissions. It's not quite at the level of the energy cost for the coal gasification SMR, but it's getting there. So with more reactor optimization, a better reactor design, we can go there. But it is competitive with thermal plasmas, for example, Monolith's one, and the thermal pyrolysis one from BASF. In addition, we also produce carbon, primarily multi-layer graphene, and with only a tiny amount of amorphous carbon, whereas they primarily produce carbon black. So for the plasma modeling, we developed a 0D kinetics model using the Z to determine the the plasma chemical reactions and also the reaction pathway. To do this, we use the ZD Plaskin module using a Boltzmann equation solver called Boltzig Plus. It calculates the continuity equation using the density of species over time, and calculates the reduced electric field through contingent upon the power density in a self-consistent manner. And we did this in successive time steps. Fed into this reaction types, electron impact reactions, chain branching reactions, ionic reactions, and reactions involving neutral and excited species as well. So analysis of the reaction modeling. So here we have the reaction rates plotted against the time. And initially, the primary source of hydrogen production is from the electron impact of methane, producing the hydrogen. But as the arc progresses downwards, the reduced electric field decreases, and also there are more species involved after that. So ultimately, most of the carbon is formed from the chain branching reactions of hydrogen atoms interacting with higher value hydrocarbons, which then forms the hydrogen, and that accounts for 28.6%. Moving on to the carbon. The carbon is kind of similar in terms of most of it initially is formed from the electron impact of methane, but as the arc progresses and there's more other species involved, ultimately the majority of the carbon comes from acetylene, primarily via the route of C2. So that's an interesting thing that we didn't necessarily expect from the modeling. So comparing this to some other kind of methane cracking pyrolysis technologies, there are a range of kind of reasonably large scale ones nowadays, a mixture of thermal, plasma, and catalytic ones. Two kind of the ones to focus on are probably BASF, who recently teamed up with ExxonMobil to scale their thermal pyrolysis technology, and the thermal plasma torch from Monolith. They primarily produce carbon black, as I mentioned, whereas we primarily produce multi-layer graphene with only a small amount of carbon black. So why is the quality of carbon produced important? Because if you look at this, the expected price for the carbon, for carbon black, it can be as low as $0.4 per kilogram, whereas some carbon nanotubes can be up to $600 per gram. This can vastly change the economics of your process as you develop and commercialize. So it can change how you kind of optimize which process you choose, etc. And it's probably economically more important than the hydrogen. Of course, you also need to consider the market size, because you can't sell carbon to a market that doesn't need that much carbon. But potentially, if there are more carbon nanotubes or more graphene available, then the market can grow to meet that demand. So in conclusion, we developed plasma-assisted methane cracking demonstrated the cogeneration of CO2-free hydrogen and carbon nanomaterials under ambient pressure and temperatures with an optimal 14 kilowatts per kilogram of hydrogen and a carbon selectivity of 83%. The majority of the carbon was multi-layered graphene and a small amount of amorphous carbon. A detailed reaction mechanism for the plasma-assisted methane pyrolysis was developed using the RGA reactor and was proposed and validated against our experimental results, and the validation matched relatively well. It provided a deep understanding into the formation pathway of hydrogen production and the carbon yield. Thanks, and I should also thank Dr. Bowen Liu and Dr. Jintao Sun, who were our previous postdocs who led this data.
Once the side reactor cracked the methane into solid carbon and hydrogen, as you saw the conversion, you need to do the recycling and purify the hydrogen. So my PhD student will talk about purification by PSA. Another task that University of Stavanger had is to look at the carbon that is produced in the reactor and how does it look with different scenarios. So today I will talk about methane cracking, a green route to ultra-pure carbon, and I will show at the last slide, you will see what I mean by ultra-pure carbon. That's outline, methane. I think already the previous talk have touched upon what is this about, methane cracking into solid carbon and hydrogen. You got methane, you will break all the bonds like Theria did physically with the model, and you get 3 kilo of carbon and 1 kilo of hydrogen for 4 kilo of methane. The thermodynamic, this reaction is endothermic. You have to give energy to the reaction. And that's why when there is no catalyst or there is no smart plasma, then you need to do this reaction at very high temperature, 1000. So that's what you see typically done at 800 to 1200 degree. Entropy change, because we make more than one gas molecule, there is a positive entropy change that brings also, like, it favors at high temperature and low pressure. So equilibrium shift toward the product at high temperature and low pressure. The energy source can be different. Now in case we are using sustainable way is a plasma, but you can use BASF and other companies that were mentioned in the previous talk, they can use thermal energy as well. This is what is today existing, or this is what is known today, how you can crack or pyrolyze methane into solid carbon and hydrogen. You have catalysis process, they bring the temperature down. You have molten metal pyrolysis, microwave. And the question was like, what is the difference? If you use a catalyst, you have lower temperature, but the carbon get contaminated. So it has maybe limited use. And when you want to make a pure carbon, maybe there is a different need. If you are aiming at carbon nanotubes, then you can think of using a special process to make the nanotubes also. But it's in plasma, it seems like you can tune it at a certain extent, the type of carbon that you can make. So what you see is a non-catalytic, high temperature. With a catalyst, you can go down, and if you put non-thermal plasma, it will be further lower temperature. So if you want to know more about catalytic cracking of methane, Professor Jichin Yu is sitting here. He has been doing this research for a long time. And also, yeah, some of his PhD students also are here in the audience, and they know. They are working in Elkem or other companies. Christian is here also. So non-thermal plasma in the category of plasma pyrolysis. So there is microwave, there is a combination of microwave pyrolysis and plasma. Also there are other projects are represented here. They were sister project along with ColdSpark. They were using different plasma process to crack the methane. So mechanism, Jonathan discussed about how the methane is going into, you start from a gas molecule and then methane forms bigger molecules in the process, and those are getting cracked into carbon, yes? Without going into detail, but this process seems to be temperature sensitive, different reaction path will form. So you don't end up only solid carbon, you can produce also other hydrocarbons. But the question is how much these are produced. And so how do we control the conversion to the hydrogen and carbon and have minimum of this side product? So that's what side is doing. That's how the temperature affects the type of product distribution that you will have inside the reaction. The main message is that the C2 gases, when they are formed, abstraction of hydrogen from those gases leads to carbon formation. And they will come out in the reactor. You have now complete convergence. So the probable gaseous product that is going out is not only hydrogen, it will have acetylene, ethane, and unreacted methane, and some other hydrocarbons. So the difference between Liverpool work and now what Said is doing, they have extremely good GC, so they can analyze lots of different products that are coming out, so get a better understanding of what is happening in the reaction. So that's the work happening at site. Carbon, everybody knows carbon, have single nanotube, fullerene, a black carbon, there are different kind of carbon allotropes, and you heard about the nano domains of graphene and graphene or graphite that Jonathan mentioned. The market for carbon is quite big, I would say, and today the needs are met from fossil fuel, so there is emission associated with the current carbon production. In IREC presentation, you will see what is the environmental footprint. For 1 kilo of carbon, you produce probably 3 to 5 kilo CO2. And so if it is a tire industry that is using huge amount of carbon, that's a huge amount of CO2 footprint that's associated with it. So these are the numbers you can see. Tire, high-end product, ink, and nanotubes are also useful for many applications. And the tire industry have a goal to be emission-free or green, so that Goodyear's and other tire company, Michelin, they are competing with each other to create a sustainable product. And they are looking at better carbon for their application needs. So that's the carbon black, and here you see the C and T. Jonathan mentioned the price difference between them, but also the requirement of the market size is different. And so I think the ColdSpark or technology that is developed now, it's a modular technology, so you can scale it up. Scaling or adapting to the processes also makes it easier to implement. Now, this is the conventional way of furnace black carbon. Natural gas is fed into the furnace, and then you separate that's the feed mixture. You have different things coming in, and you get at the second water quench baghouse, you get the carbon produced, carbon black. That's a typical today's method use. Here you see the CO2 emission and the cost per ton. So roughly we are talking about 3.5 kilo of CO2 per kilo of carbon, and using the conventional fossil fuel. So there are different ways you can reduce the CO2 emission, but that's being the dominant technology today. And not only the CO2 emission, but you have other gases also emitted with the conventional technology. And the efficiency is not there also, 39 to 40% efficient, the current process. So the carbon, if you take any organic waste and heat it, pyrolyze it, you will make a carbon. And that doesn't make it useful for all these kind of applications. So there are properties and structure have to match. And so if you look at the list of carbons that are known today, the number and the tire industry is using, you will find hundreds of them classified. They label them as N22, N11, 3, this different naming code, and that depends on the properties of carbon. So they have classified their carbon into based on their morphology and structure, properties, and their needs. So if you want to improve tires with certain things, they need a specific types of carbon. For cement industry, if they want to mix in the cement, they need a specific type of carbon. There are needs also, Elchem is here, and they have also specific needs in the metal industry, what kind of carbon they want to use it. So not every carbon gets to the end use. So these are what typically is characterized. So use a Raman spectroscopy to look at the, so you can see here, these are the different kind of carbons and what kind of differences you expect if you characterize them using different techniques. This is done by yeah, this is carbon black by microwave plasma methane pyrolysis. This is one example. You can see the TEM image, kind of sphericals, and there may be, so you see the layers also there. That's coming from transmission electron microscopy. So you look into depth closer to electron diffraction and details of the structures. Here is a Raman spectroscopy where you look at the D band and G band. That is a typical feature for carbon. You look at how defective is your carbon. And higher the ratio, higher the defectivity. Means you have lots of amorphous carbon. If you have pure graphene, you will see only G band. This second peak will not be there. So that's an example to look at the purity. This is commonly used technique. What you see here is we are heating the carbon in air at a different temperature and see at what temperature it gets oxidized to CO2. It burns off. Okay? Higher the temperature, more graphene type of carbon, higher structure stability. So they show that this microwave plasma and they compare the different kind of carbon. So it's coming quite high stable structure. These are the CNTs. They are made by the pyrolysis in fluid catalytic bed. That reference is here, you can see. And again, we are looking at the D and G band, like similar to this Raman, and also the stability. So because this is a process, things are changing eventually in the catalyst. So you need to work out the process of regeneration. Yes. So that's the thing with the catalytic process, that at one point you will have to take care of your system and bring back to it alive or refresh it. And so it works again. In a plasma process, there is no catalyst. So that's a different advantage it's offered there. Yes, this is the work at UIS. Professor Jichin Yu has been doing that, making the carbon nanotube using the catalyst and doing the catalytic cracking, single step, CO-free hydrogen, and very simple and flexible. You can see the results. We get very well-defined nanotubes formed on the catalytic system. And there is a poster outside. Thomas is here, the PhD student currently working with me and Professor Jichin Yu. You can look at the poster and get more details about catalytic process. Now, how is the carbon? Sorry for the animation, that's me, last minute. So the carbon coming from ColdSpark, you can see the images here. So it's also spherical, spheroid, ellipsoid, but some places we see the graphene sheets, some parts. So it's a mixture of, like, you know, in the Liverpool work, they saw more graphenic and less amorphous, while here we kind of see more amorphous and less graphenic. So there is a difference also there. This is a scanning electron microscope. So these results that I'm showing here, these are the results tire industry is asking. We want to see these properties, and according to the ASTM standards. So we have to characterize following the standards. There is one more thing that they need is oil adsorption number, but that is related here. So what you see is this morphology, how the carbon particles are agglomerated. Are they easy to mix, or what is the nature of the particle and size? So we analyze them. If they are, you can see the particles. We can measure each one separately, and they are coming 130 to 140 nanometers. And then this is the surface area. This is a specific surface area measured using nitrogen. That is also the property they use quite in the tire industry. They like to compare this specific area with the oil adsorption number, and then they decide whether the carbon is good for improving elasticity or other properties of the rubber, and so as additives. So it's quite a good 101 meter square per gram. That's what we have been getting. And the Raman part that I represent, you got the D band and G band. So it's amorphous carbon. They are not well separated, but there is some sign of graphenic carbon also from the TEM. And the stability is quite good. It's stable to 600. This is thermal oxidation stability. And what happens here in the second step, everything is burning. It gets burned off to CO2. If you take plant waste or municipal waste and burn it, the last step here, you see this is a percentage weight loss. the last step here would be like around 40. So you get 20% ash after burning. In this case, everything is burned off, nothing left. So it's just a carbon. Yes, that's where I make the comment like a purity of carbon. It's very pure. You can get similar kind of carbon if you use a plant waste, there's biochar, but sometimes you still end up with impurities at the end or the ash at the end. This was also the recent result that we have, that in their large reactor, they have been able to make the carbon filaments. So before I showed is a spherical ellipsoid particles, but now they see the filaments formation in the reactor. And when we look at the composition, is also very pure. You can see the comparison between the carbon black that I showed in the last slide and the filament. Filament is quite more stable. The red curve is coming from filament, so it is temperature stability is very high. But the purity wise, they both are 100% carbon, pure carbon. So that's an example where I can see the two different types of carbon morphologies coming. So before we saw amorphous, little bit of graphene, and now we see filaments. And this is not done only in a lab scale. This is done in the big reactor that you will see later in the afternoon. So there is still more work to do to tune it to that we will discuss later in panel discussion. What are the next expectations are coming here? But it's possible to tune this process. So thank you for your attention and open for question. This is written by my postdoc who did most of the characterization. So I don't take authority on that one. So you can see that when you see today demo. So when there is a discharge happening on the electrode tip where there is a curvature and high electric field, that's what I learned yesterday. So you have the growth of the filament, and that filament is also, the initial formation is also contributing to the growth, and then that is falling. We have seen also the filament growth not only on the electrode tip, but also on the surface there. And that's something we are trying to understand. I think that's what my understanding was yesterday. Yes. So there is concentrated electric field on the tip of the electrode that creates the first nuclei to grow, and then that growing into the filament and then falling. That's the mechanism. Yes, he's clapping, so he approved it. He's approved it. Yes.
Looks like it's some kind of riskier structure where we have a dislocation center or screw dislocation. Yeah. Could be. We have to study that. We got the first few batches from them, so we will investigate further into. So what you're saying is that you actually produce this type of carbon structures directly from the reactor.
Yeah. This is nothing done after. This is all coming out of the reactor. We have not done anything else. But there is yes. This is all coming from reactor. No post-production processing.
Have it been tested for an application?
No. Me personally characterizing, the site is active, so I don't know if what they have done with the material. They might have different projects and things are going around. So if you want to add, if there is.
Yes, the frame of the project was more focused on the hydrogen from the application side, so we are a bit constrained on what we are allowed to investigate during the project.
How can you tune the process to get more filaments compared to amorphous?
Yeah.
And is the amorphous produced from the filament? If you think that it's not.
So yes, I could see in the video the filament was there. I don't know, today we will have video in the presentation. You will see there. So the amorphous part was happening also at the same time when the filaments were growing on the side. So this seems to be a mix. Maybe the amorphous. Yes. We could see that like the amorphous floating in the air while the filaments were.
So it's almost unavoidable to have a mixture?
Well, we can keep it in more the growing phase, but that is more energy intensive. So if you're focusing on producing the cheapest possible hydrogen, you will not go into this route. But if you're focusing on creating the most valuable carbon, this is another way we can operate.
Is the shape of the electrodes so to get more filament?
Yes, and also the geometry and how large the filament can grow before they are creating problems and being collected. And so these are all things we are investigating and have on the block.
Okay. You have a question? We are now on the. We are running over 1 minute now. Yeah. Okay.
If you want to boost the C2 molecules compared to hydrogen and carbon, what would you do? What do you need to do? Is it the residence time? Mostly.
Yes, the faster we run
You
through the reactor.
question, us behind didn't understand the question.
Sorry, I can give you. This is on. This is on.
I was asking how is it possible to boost the production of C2 compared to hydrogen?
Well, it's controlling the residence time inside the plasma. So the slower it goes through, the larger, the further the reaction happens. And by adjusting the residence time, we could more freeze the process, producing more C2 hydrocarbons. So that is what we have been seeing, which causes problems in the downstream process when we were expecting pure carbon and not the longer chain hydrocarbons, but that's another issue.
Okay, so you're saying that if you boost C2, you get lower purity carbon?
No, but you get the longer chain hydrocarbons that they plug up filters and create different problems. Yes.
Okay, let's move on. Next speaker is Ashika Dilshani. She is a PhD student at the University of Stavanger. She has just completed 1 year. She is also working associated with high value and in ColdSpark.
So when it comes to methane splitting, like we talked about it earlier also, so you will crack methane into solid carbon and hydrogen. However, you still need a gas separation and purification unit to obtain high purity hydrogen. So there are several methods to purify hydrogen, like pressure swing adsorption or membrane separation or cryogenic separation. They obtain high purity and also high recovery rates. So yeah, when going to the PSA, we have to do several steps. It's not just starting the cycle. First, we need to characterize the adsorbents for us to know if it is suitable to go for the next step. So we characterize these materials like activated carbon zeolites. Mainly we need to know the surface area and the pore volumes so that we know it has the ability to adsorb gases more than hydrogen. So, for the after the characterizing the material, we have to go with the adsorption isotherm, which is done in the equilibrium state. We do it in the specific temperature, wherein the pressure. So here you can see that carbon dioxide has high affinity and also methane, but very low affinity for the hydrogen. That means we can separate hydrogen based on these affinities. After the equilibrium state study, we do it in the dynamic study because the PSA runs in dynamic situation. So we in the PSA we need to stop the adsorption step before the column saturates. So we need to know at what time it will saturate. To know about these details, we are doing this breakthrough study, and this breakthrough point is more important because that is where we need to stop the adsorption, actually before that. After that, we do the PSA cycle, we define the different adsorption step and then do the cycles and analyze the different effect of different flow rates, temperature, pressure and etc. So after this PSA, we do the This is for the lab scale, but what about when you are scaling up the process? So that we need the simulation. We are using Aspen adsorption. In there, we need to validate the model that we are using. For that, I have validated the model with the experimental breakthrough study and the simulation. So you can see it's quite a good match here. With that, we can validate our model. After that, we can go for the Aspen simulation. So these are some of the experimental results. This experimental results and Aspen simulation I have done for the 20% hydrogen and 80% methane that I have mentioned earlier, that most of the studies are focusing on having more hydrogen in the feed gas. But here we had a challenge having 20% hydrogen. To obtain high purity hydrogen, we did the experiment and the simulation. Both showed 99.9% purity. So that even though it's a challenge, we think we managed to get the high purity hydrogen with this setup. And yeah, then I also simulate the different composition, having different compositions in the feed gas, how it will affect with the PSA. So for that, you can see having more hydrogen will not change much about the purity, but how recovery will increase considerably when having more hydrogen in the feed gas, and also the productivity. And actually what I want to say is the steam methane reforming is the most common widely used PSA as for today, but it comes with the CO2 production and emission, and the methane splitting is there is no direct CO2 emission. However, it still requires a purification, separation and purification unit where we can use PSA. It's an economical process and viable process. Even with that, when we even though it's a economical, we can obtain high purity hydrogen having the PSA and working it in different configurations. Yeah, thank you.
Torbjörn he was in the work package 5 leading the work package 5, and he will show the ColdSpark process model validation and industrial upscaling. Yes.
Okay, so as Sachin mentioned, my name is Torbjörn Grønn, representing Norse Energy and Technology. And yeah, we've been doing more of large-scale overview of the system rather than digging into the carbon properties and hydrogen separation. Yeah. So there were 3 tasks for the ColdSpark work package 5, which was a small-scale process flow modeling, and industrial scale upscaled, and a system optimization for energy and material consumption and high value yield, which is an even further upscaled version of the model. So in the application, this was defined as the setup. Do I have a pointer?
The line. On that side. Do that.
There?
On the screen. Yes.
Screen, yeah. Not pointing at my screen. Okay, so we have a methane feed going into reactor with connected to the power supply. Carbon is collected through the reactor. We have an outlet gas stream consisting of hydrogen, methane, and other byproducts formed in the reactor. So hydrogen is separated, and the unreacted methane, leftover hydrogen, and byproducts are recycled back into the reactor. So this is the first model that we built, small scale. So we see a methane coming in from the left. We have introduced some piping for gas velocity calculations. We have the reactor, and we have some GC and separation of hydrogen, which is, for those of you familiar with HYSYS, it's modeled as the component splitter, and the split is defined based on Ashika's work from the previous work package. And there is some rest gas, which for future models would be recycled back into the reactor.
Work from work package 6 that was focused on the environmental and economic assessment of ColdSpark process. And so why, like the other presentation, were more technical, and thanks, like I really thanks that they are technical, so I can skip that part and go into the performance and focus on it. So as you can see, my speech will be divided in 3 different steps. The first one will focus on the environmental performance. Then I will revise the EU policies on methane splitting process. And at the end, I will evaluate the economic potential of ColdSpark. But first of all, let's start with the environmental pathway. And let's define which is the methodology that I apply to evaluate the environmental impact of ColdSpark. What I use is life cycle assessment. Life cycle assessment is a worldwide recognized methodology that define the impact of a product or process through its entire life cycle. It is the basis, I think that you know well about the carbon footprint. The carbon footprint that I think maybe you calculate even by yourself, like your self-carbon footprint, or as well I did. And it's the base of the European Green Deal. How can we define that something is sustainable? One of the strategies that European Union is using is the life cycle assessment. So, but how we apply the life cycle assessment to ColdSpark project? Our aim was to be comparative. Like we cannot, we can, but it's not that useful to define the sustainability of a process at its laboratory scale, because how can we compare something that is laboratory to something that is industrial? So our aim was to define which is the life cycle assessment of industrial scale of ColdSpark process. And to do so, we have to look behind the 2025 to go to the future years. And we define 2 different scenarios, which is the 2030 and 2050 scenario, in which we various the future electricity mix and as well the process technical performance. But let's be more clear about what we did. First of all, our objective was to identify the environmental impact or performance of ColdSpark process and compared it with the benchmark hydrogen production process and carbon production process. To do so, we used 2 functional units, so one kilogram of hydrogen and 1 kilogram of carbon. The scope is cradle to gate. So what are we taking into account? We are taking into account the emission from the input, and we are taking into account the emission from the process itself. We use 2 geographical locations, Norway and Germany, and we use the foreground data from the process simulation, what was presented before by Norse, and the background data from EcoInvent. It is a data set for LCA experts. Here, a graphical representation of what we did. This is our system boundary of our process. So we are taking into account input, the emission from the input, so electricity, natural gas, water, and the bill of plant, and then the emission from the process itself. And we compare different processes, as you can see here. So steam methane reforming, which is our baseline, steam methane reforming with carbon capture and storage, autothermal reforming with carbon capture and storage, and water electrolysis, which we use the proton exchange membrane water electrolysis. So another important point is that it's hard, sometimes we speak about environmental sustainability, but what is specifically? So we have, for sure, we know that we have to take into account the climate change, because we are doing the energy transition for the climate change, but we have not to forget all the other impacts that we can have. So here are a list of the impact categories that we analyzed that are based on the EU suggestions. And first, finally, let's have the results. Okay, here, first of all, we have the Norway case for both, okay, 2030 and 2050 scenario. And what we can see is that for both hydrogen and carbon production, the lower emissions are obtained with the ColdSpark process, which is the non-thermal plasma methane splitting, even lower than water electrolysis for both 2030 and 2050 scenario. Then, going to Germany, the situation is a little bit different for the 2030 scenario. Why? Because as we can see, the processes which are based on high electricity consumption, as water electrolysis and non-thermal plasma, in this case, we have higher greenhouse gas emission related to the high upstream emission of the Germany electricity mix. But going to 2050, where the electricity mix will be based on renewable energy, as well, we can see the non-thermal plasma methane splitting is gaining as the best technologies from the greenhouse gas emission assessment point of view for both hydrogen and carbon. Then let's focus on all the other impacted categories that we analyzed. As you can see from this table, we normalize the results according to the baseline, which is the steam methane reforming. And here what we obtain is quite interesting, because if from one end we are decreasing the greenhouse gas emission, on the other hand, we have higher impact in all the other categories, especially for the water electrolysis. Why? Because we are using high electricity, there is a high electricity consumption, and on the other hand, due to the presence of critical material inside the electrolyzer. But in this scenario, non-thermal metal splitting, as well, is well performing, because even if we have high electricity consumption, we have to remember the multifunctionality of the process, because we are not only producing hydrogen, but we are producing hydrogen, carbon, and this system, considering the simulation from Norse, we are considering the production of acetylene as well. So even if we have high impact in some categories, we have to split the impact according to the different byproducts that are included in the process. And another important point is that we have no critical material. So for this reason, we can gain against the water electrolysis and be comparable with the reforming process with carbon capture and storage. But our results are based on the simulation assumption. So let's see how sensitive is the results of our LCA according to the assumption that we define. To do so, we change the reactor power requirement, the methane conversion efficiency, and the allocation approach. As we can see, according to reactor power requirement and the methane conversion efficiency, even in the worst scenario, our change is not that high. We are still close to 1 kilogram of CO2 per kilogram of hydrogen. That's because we have still we have low emission from our electricity mix, as we say, because it's based on renewable energy, and because for the methane conversion efficiency, if we go to lower methane conversion efficiency, from the simulation we will have more carbon and acetylene. So this is a rebound effect. We will allocate less impact to the hydrogen because we are producing more byproducts. But this is a really interesting point, is the allocation. In the worst scenario, in which we are allocating all our emissions only to the hydrogen, this is the worst case. That is, in any case, it's less than 2 kilograms of CO2 per kilogram of hydrogen. So this is a crucial point for the environmental performance of ColdSpark process and all methane splitting process. And then we can see that better in the EU focus policies. It was only in July, the first week of July, that the EU finally gave us an annex for the greenhouse gas emission guideline for low carbon hydrogen. So now we know how we can calculate the greenhouse gas emission of hydrogen based on fossil fuel. And in this guideline, there was the methane splitting as well. And what is the results from this guideline are quite interesting, because for the EU, we have to include in our emission assessment the emission from the end of life of carbon as it is combusted. So we have to include the combustion of our produced carbon. So if we are not sequestering solid carbon, that means that we will overcome the EU carbon emission threshold of 3.2 kilograms of CO2 per kilogram of hydrogen, going to more than 4. But if we are sequestering our solid carbon, that means that is stored or used in cement and asphalt application, that means that we will be again below. And then there is another interesting point to analyze, which is the use of biomethane as feedstock. But to explain this, let's do a brief introduction, which is the life cycle of CO2, biogenic CO2. So when the plants, in order to produce biomass, they are capturing CO2 from the atmosphere. And then at the end of their life, they will release through the decomposition that CO2 again. So the carbon life, we can define that is at 0. We are capturing and we will remitting. But if we are not more emitting this CO2, if we are sequestering this biogenic CO2, in this case, we can go negative. We can say that we are removing CO2 from the atmosphere. So European Union gives a value of -1 to the gaseous CO2 sequestered. So let's see what are results. Well, they're interesting because even if we are sequestering the carbon, our value will be the same. Why? Because Union does not give carbon credits to the solid carbon. It's not recognized as a sequestration method. And if we are recognize this as a sequestration method, well, we can go negative. So biomethane splitting can be a carbon removal potential technology. Then the techno-economic assessment and the levelized cost of hydrogen. Here on the left, you can see the technical and economic consumption. It was always an industrial scale. What I want to remark here, and that I considered energy and natural gas EU median price. And we consider as well the revenues from carbon, acetylene, and energy trading system. And we calculate the levelized cost of hydrogen. Here, the results. Considering energy and natural gas price in line with the EU media, the results that we have is that we go our process is competitive with water electrolysis, but still higher than reforming process with carbon capture and storage. But there's a big point here. In this analysis, we consider the ColdSpark as a hydrogen capacity, which is comparable with water electrolysis. But if we have a hydrogen production that is comparable with the reforming process, so if we are consuming more natural gas, so we go to higher band consumption, you can see this green line. Well, ColdSpark process can be comparable with steam methane reforming and lower than steam methane reforming with carbon capture and storage. What we did is again a sensitive analysis of our results, and again we can go below or close to €3 per kilogram of hydrogen if what? If we have high natural band consumption, if you have electricity price that is comparable with Norway geographical location, and if according to the carbon selling price. As well, if we have a kind of a carbon allotropist that has a higher cost, we will have higher revenues, so our cost of hydrogen will decrease. But as well, we have to pay attention of the methane conversion efficiency that has to be at least 20%, to the reactor power requirement, as well as I said, the geographical location and the revenues. So let's bring a very fast resume. ColdSpark process can be competitive with hydrogen and carbon production process from environmental point of view. The solid carbon and its use, it's a key to define if methane splitting can be a low carbon hydrogen process. And when we are using biomethane, that can be considered, we can go negative. So we consider carbon removal potential of this process. While for the economical point of view, ColdSpark can be competitive with steam methane reforming, but we have to be very careful into the definition of the geographical location, and as well for the future research in the electricity consumption requirement of our reactor, and as well for the methane conversion efficiency that has to be at least 20%. Thank you.
So we have been at in total at 17 national conferences and trade shows. That was smaller or larger, and at 23 international conferences. So I think we cannot really pinpoint this. For some events, we don't have the real numbers. So, but just an estimate. Sometimes Michael spoke in front of 2,000 people, sometimes it was only 15. But I think that we reached through these activities around more than 5,000 persons, and then another maybe 600 to 700 within our own activities on trainings or conferences that we have organized. So, for example, we handed out brochures to every single person that came to our events. We interacted on LinkedIn. We sort of took the message from the main ColdSpark newsletter, added them to our newsletters, and yeah, that was a very interesting journey for the IBBK team, because at the beginning of the project there was a lot of skepticism. I mean, hydrogen was sort of known. We had the first SMR-based hydrogen production on a biogas plant in Germany installed around 2022. So that was in the sector quite a long discussion. No, not long. It was a lively discussion a little bit. The solid carbon was okay. Does it work? A lot of skepticism. And also the discussions on what do you do with the carbon in the end. So if you put it in tires and tires are incinerated after 3 to 4 years of use, then it's still CO2 emissions into the atmosphere. So we had a lot of discussions like this. But at the end of the project, when I sort of talked to I met the same people again at the beginning of October on a German national conference, and I had a bottle with the black fluffy stuff to show. It has changed, and so hydrogen is not the hot topic anymore. It's considered to be a fixed part of the energy mix in the future. Or it's also being discussed as a intermediate element. So, for example, to use CO2 that is cleaned out of raw biogas when it's upgraded to biomethane, combine this with hydrogen to methane again, use the methane for something else, or split the methane, have the carbon and have the hydrogen back to convert it with the CO2 that comes from the biogas upgrading. There are other technologies that are other startup companies that use this hydrogen and the CO2 to make e-methane, artificial methane, and use it for a different process. So I think this gives new opportunities. The interest in the carbon and the carbon properties has increased throughout the year, the project, which is nice, has been nice to see. But what the people we talk to still emphasize, those that come from the biogas and biomethane sector, for them is often, especially for the research, it's important to have a long-term CO2 storage to be carbon negative, to have not to have pathways with this carbon that releases it after 2 or 3 or 5 years again into the atmosphere. And also with the change in the German support system for biogas plants, the ColdSpark technology raises interest as a future opportunity, and there are already interests of operators to visit the test site, so that needs to be discussed, which is also something that was not clear at the beginning, whether this would happen. So we are very happy and optimistic that we were part of the project. And the lessons I've learned, I mean, it's a bit of the lessons learned personally and from the team. One of the first slides that Talia presented was this calculation, the energy demand and the CO2 emission space compared from methane splitting and water electrolysis. And that was a good start for discussion with the sector. It really opened up sort of, ways to discuss. And also, what Isabella said before, the location is key. It does not make sense when you have high CO2 backfires or upstream emissions that relate to power or natural gas. And this has been really a change to have a product to show. So I think what helped us also compared to other projects where we had the same task before, we started early this time, just from the second month of the project to the end, and sort of prepare the ground for the discussion. And also now when there are results, it's not a big surprise, but continuous story. Yeah, and I was also found it interesting that the long-term benefits, especially in the biogas and biomethane sectors, play an important role.
When people see ColdSpark again on the social media or somewhere else or during the events, they remember who we are. So the storytelling has the advantage of clear narratives. It bridges not just science and industry, it bridges people. We have a recognition, we build brands, which is quite important as it has the high mission to go to the market and they will really do it. And as a result, we receive rapid growth in audience and the real impact.